Okay, in this presentation we are going to do a correlation analysis. So here's the scenario. An interview panel has two members, and member A and member B. And these two members have scored a large number of applicants on a scale from 1 to 40 with the purpose of ranking the applicants according to their suitability for a job position. The scores for a sample of 12 applicants are given below, with SA and SB denoting the scores from panel member A and B respectively. So we have the A scores, which are saved as SA, 35, 14, 28, 33 and so on. And B scores 38, 18, 25 and 30 and so on. So there's 12 scores each for each applicant, for each interviewee, okay? So what we're going to do is plot a suitable graph for assessing the agreement of the two sets of scores for the two panel members, comment on the agreement in the two panel member scores based on the plot in exercise A, calculate the Pearson correlation coefficient R for these data, and then D, calculate the Spearman rank correlation RS for these data. And then next, Kendall's rank correlation tau for these data. Comment on the suitability for these three correlation coefficients used in exercises C to E with respect to the purpose of the scoring. Perform 3 statistical tests for a suitable hypothesis test of no association between the scores of the two panel members using one of the correlation coefficients from the previous exercises for each test. So we're going to do a Pearson test, correlation test, a Spearman correlation test, and a Kendall correlation test successively. For each test, your answer should include the p-value and a conclusion. And finally, comment on the validity of the tests used in exercise G for testing these hypotheses. Okay, so essentially what we're going to do here is, this is just a broad description of the problem. We're going to visualize the agreement using a graph, calculate the correlation coefficients, do some hypothesis testing on this to determine the significance of the correlation, and then interpret the results. So this is just the set of skills we are developing here. So let's get into it here. So what I'm going to do first off is create the data sets here, SA and SB. Just set them up as a vector, a numeric vector in R, and just save them there as SA and SB. And we're going to use those two vectors of numeric data on an ongoing basis. Okay, so exercise A, what we're going to do here is plot a suitable graph for assessing the agreement in the two panels. Okay, and so a scatter plot is suitable for this purpose. So plot SA versus SB. SA is on the x-axis, SB is on the y-axis. Just importantly, when you're carrying out this sort of analysis, or particularly when you're creating plots like this, it's very important to annotate them extensively. So always have a title and an x-axis label and a y-axis label. Additionally, what I'm going to do here is just specify the plot characters that I'm going to use. Plot character 19. I'm going to make a big CEX controls the size. I'm going to put it as a 2.4, and I'm going to have it colored in blue. What I'm additionally also going to do is add a regression line over the plot. So abline, and I'm going to fit a linear model with SB explained by SA. Remember that SB is their Y variable in this case, and SA is the X variable, and I'm going to color it in red. So that creates a very extensive plot there. Now, I probably made those plot characters, those little blue orbs, a little bit big, but I just wanted to sort of make this plot as easy to follow as possible. Now, overall, there seems to be a broad agreement, as in the plots, the points do overall follow that red trend line there. So I reckon it's fair to say that there is some degree of agreement in the scores between panel member A and panel member B. Okay. So I believe that is the exercise B, actually. General guidelines. This is for all types of plots that you might have encountered in such a situation. If the points lie close to a straight line, in this case it's the regression line, it indicates good agreement between the scores of the two panel members. The regression line helps to visualize the trend. If the points scatter widely around around the plot, it indicates poor agreement. So let's look at the plot. Go back to our plot. I'm sticking with my original assessment. I'm just recalling that we are not plotting from the origin, partly to assist the visibility of the plot in this YouTube video. But if we had the plot going all the way down to the x-axis and the y-axis, the proper x-axis and y-axis, it would be more emphatic. My conclusion. The conclusion is this plot indicates a fairly strong positive linear relationship and hence broad agreement between the two panel members. Okay. So the Pearson correlation coefficient is simply COR, that's the command, COR, and name the two variables, SA and SB, the two vectors. What could happen there is I could specify method equals Pearson, but that is actually the default method. Anyway, Pearson R, that is the Pearson correlation coefficient R, and it is 0.753667. Just to 3 decimal places, 0.753. Calculate the Spearman rank correlation coefficient, RS, for these data. Okay, so just to sort of flick back there, there's an additional argument here that says method equals Spearman. So you could do that here for method equals Pearson. This is the Pearson correlation coefficient, the previous case, but it's the default setting. If you're using Kendall or Spearman, you just have to make this additional input argument. Method equals something, Pearson, Spearman, or Kendall. Anyway, Spearman's RS or Spearman's RS, cor, SA, SB, method equals Spearman, and there we have it there, 0.6853. Okay. And Kendall's tau. Okay, Kendall's rank correlation coefficient tau, and again, Kendall's tau is correlation coefficient COR of SA and SB, method equals Kendall. And there we have the value there, 0.515151. Okay. Comment on the suitability for these three correlation coefficients. Well, Pearson's correlation coefficient measures the linear relationship between the scores. Okay. Spearman's rank correlation coefficient measures the monotonic relationship between the scores, which is useful if the data is not normally distributed or if the relationship is not linear. Okay. Now, there's an argument to be made there that this data set is not linear, or not normally distributed, I should say. Okay. Kendall's rank correlation coefficient also measures the ordinal association between the two quantities. It is less sensitive to data with large discrepancies or outliers. Okay. So, anyway, that's grand. I'm not making any assessments about if there's any big outliers in this, because there's only 12 values. Okay, so there's only 12 applicants in this data set. So, perform 3 statistical tests with a suitable hypothesis of no association. So, essentially, here we test whether there's no association, which is our null hypothesis, between the scores, and we're going to use the 3 different correlation coefficients. Okay, so in each case, the null hypothesis H0 is that there is no association between the scores from panel member A and panel member B, and the alternative hypothesis is there is an association between the two sets of scores, and we'll be looking at the p-value. A low p-value will indicate that we should reject the null hypothesis and indeed conclude that there is some sort of association. So, the first one, the Pearson test, cor.test, SASB, method equals Pearson. I just stuck it in this time. Test using Pearson's correlation coefficient. So there we have all the output there. We have 95% confidence interval, which does not include 0 in the range of values. But anyway, what I'm really looking at here is the p-value, just for the sake of brevity, which is on the second line of the output on the right-hand side, not including the header. P-value equals 0.004642. So in this case, we reject the null hypothesis. This indicates that there is an association between the two sets of scores given by given to each applicant by the panel members. Okay. So p-value is less than 0.05. Reject the null hypothesis. We're going to conclude that there is association between the scores. Okay. And that's how you might extract it there. The $sign p-value, just actually explicitly extracted out of the hypothesis test object. So we're saving it as Pearson underscore test. That's the test object. And we want to take out that value in particular. So we go $p.value. And that brings us to that value specifically. Okay, now the Spearman's rank correlation coefficient test is very similar. In fact, cor.test SASB method equals Spearman. Again, we are looking at the p-value. Okay, so it's on the second line of the output. P-value equals 0.01731. Okay, the alternative hypothesis and the null hypothesis are pretty much the same, broadly speaking. The output is slightly different. There's no confidence interval, but essentially we are looking at the p-value. It's the one thing that stays consistent between the three tests. And we're going to save that test as Spearman underscore test, and we're going to extract the p-value, and there we have it again, 0.01730. Okay, and again, the p-value is less than 0.05, so we reject the null hypothesis and conclude that there is an association between the scores based on the Spearman's rank correlation coefficient. And finally, Kendall's rank correlation coefficient. Very similar structure to the Spearman. Here the p-value is 0.02098, and that is what we're interested in. And just following the same approach as I have used previously, we save it as a model object, and we can extract the p-value directly, and there it is again, 0.020980, etc. The exact same conclusion once again. P-value is less than 0.05. We reject the null hypothesis, and there is an association between the scores. Alright, so that's a lot of work done. Comment on the validity of these tests. Well, the Pearson's correlation test assumes linearity and normality, which might not be suitable if these assumptions are violated. Spearman's row test and Kendall's test are non-parametric and do not assume normality, making them more suitable for ordinal data or data with outliers. So that's it all done.